Hello, thank you. It's a pleasure to join you today to talk about some of my favorite planets in the solar system. These are the ice giants, the outermost large planets in our solar system. And I thought I would share with you some of the mysteries that these planets hold and talk about some of the things we want to explore out here. To give you a sense of why we call them ice giants, there's this cartoon that shows you the major classes of planets in our solar system. We have terrestrial planets like our own, and you've been hearing a lot about studies of Earth and remote sensing of Earth, Mars, Venus, and Mercury. We also have in our solar system gas giant planets, Jupiter and Saturn. But the ice giants are a class between. They are neither fish nor fowl. They are not terrestrial. They are not gas. They're somewhat of a mixture. And it's not just their color and their size. What's fundamentally different about ice giant planets is their interiors. They are a different class of planet. They are not composed primarily of hydrogen as Jupiter and Saturn are. In fact, we believe that they have icy mantles of what we call ices. That's an astronomical term that means water, ammonia, methane. This is not cold ice. This is warm mixtures of a slush or a slurry or a briny ocean of this material with inside this planet. So they're quite different and from Jupiter and Saturn. And one reason that we would like to explore these planets is that within our solar system, they are the least explored class of planetary body overall. And also, when we look at the planets around other stars, which we call exoplanets, what we find is that most of those planets are in the Neptune to sub-Neptune range, the green and blue bars that you see on this histogram. There are not many Jupiters, and so far we have not found many Earth sizes, although that may change as our techniques get better. So right now, the predominance of exoplanets are Neptunes or sub-Neptunes, and yet they're the least explored in our solar system. So there's a bit of a mismatch there. We'd like to change that. We have explored them once briefly, the ice giants, and Dr. Nikki Fox mentioned that mission earlier. That was the Voyager mission, launched in 1977, flew by Jupiter and Saturn, and Voyager 2 then went on to fly by Uranus and Neptune. And much of what we know today about the ice giant systems comes from those brief encounters back in the 1980s. But nevertheless, we persevere because this snapshot, this beautiful pair of images taken by the Voyager spacecraft, that's actually not what these planetary systems look like today. So I hope to convince you of that. And it's very difficult to study these planets. This is some artist representations of what the sun looks like from the surface of Triton on the left, that's Neptune's moon, and on the right, what it might look like from the Uranus system, looking through its faint ring system. And the point is that it's very far away. And that means that these planets and their rings and moons are extraordinarily difficult to study from Earth, even with our finest astrophysical assets. So let me talk first about the atmospheres of these planets. Then I'll talk about the moons and the rings and the magnetospheres, and we'll wrap up at the end. I've studied these atmospheres. This picture from Voyager was the cover of the science paper, the science issue describing the Voyager mission. And they chose this dramatic picture of Uranus because the actual picture of Uranus looked something like that, which is very uninteresting visually. It like just blank. There were very few clouds. In fact, with our image processing techniques of the 1980s, we were able to pull out roughly, well, no, exactly 10 discrete features in that atmosphere. For those of you who are astronomers, I put a bar there, 3.8 arc seconds. That's the size of this planet in the sky. And that, for those of you who are astronomers, you know that sometimes we can't resolve things better than 1 to 2 arc seconds. So it's very, very difficult to observe this planet. Nevertheless, we do. This is a picture of the Keck 10-meter telescope in Hawaii. That's a person in red inside the primary mirror of the telescope to give you a sense of scale. This is a telescope that is a segmented mirror equipped with adaptive optics. And we use the adaptive optics to remove the effects of Earth's atmosphere. So here's a picture of Uranus we took in 2004 in the near infrared. It's the H band with the adaptive optics off. But when we turn on the adaptive optics, this is what you see. And you can see in this single picture more clouds than the entire Voyager mission saw as it flew by Uranus. You can see banded structure. You can even faintly see the epsilon ring if you know where to look for it. But the point is that the planet is in fact very active and dynamic. Voyager didn't see that for a number of reasons, which we will describe. Why didn't Voyager see that? Well, as Uranus makes its very long journey around the sun, this planet Uranus is tilted over 90 degrees. It lays sideways in the solar system. And when Voyager flew by in 1986, it was at southern solstice. So the southern half of the planet was pointing at the sun. So all you saw was the southern half, and the northern half was completely in darkness, no matter how much the planet was spinning. Very unusual configuration. However, as Uranus continued its journey around the sun into our modern era, 2007 is when the planet was sideways to the sun. So it was fully illuminated. And so the entire planet was getting sunlight, just like every other planet in our system. And funny things happened, interesting things happened at that time. In fact, the planet turned on. You can see in the sort of sequence of images from Voyager to Hubble, and then taking you to our Keck images, you can see a change in the atmosphere. And that's a fundamental change. That isn't just wavelength or viewing angle. The planet's atmosphere actually turned on and became active. Very interesting. These are the best maps ever taken of Uranus. All right, this is Uranus. And you can see many dynamic structures. You can see strong equatorial waves across the planet. You can see unusual popcorn color style clouds in the northern pole, very similar to what the Cassini spacecraft saw on Saturn. And you can see very dynamic, what we call moist convective clouds. These are like giant thunderheads that rise up in the atmosphere and cause streamers of clouds. So a lot of activity in this atmosphere, really cool place. Let me turn to Neptune briefly as well. Neptune is of comparable size to Uranus, but it is even further away. So it only subtends 2 arcseconds in the sky, which is almost impossible to resolve as a disk unless you're using the very best facilities in the world. Neptune, as seen by Voyager, was already dynamic and active. The most intriguing feature was that big dark spot right in the middle of the planet, which we called the Great Dark Spot because we're not very creative with our names. I was looking forward to doing follow-up observations of that with the Hubble Space Telescope, which launched the very next year in 1990. It was several years later before we actually got around to observing because of the flawed mirror. But in 1994, we got our first chance, and lo and behold, the Great Dark Spot was gone. It was gone. It was just simply not there. And we discovered another feature, another dark spot in the northern hemisphere, very hard to see. So, I've extracted it here. So it is remarkably variable. That was only 5 years. Like, what happened? The Great Red Spot on Jupiter has been around for 400 years. Like, what happened in 5 years? Not only that, but a few years later, in 2011, Hubble looked at the anniversary of the discovery of Neptune. 165 years after its discovery, it came right around to the same place in the sky. And in those Hubble images, there's no dark spots at all. So sayonara dark spots. But then a few years later, another dark spot developed around the same location that the one that the Voyager had seen. So very dynamic atmosphere. So I just want you to understand that. The winds are extraordinary. They are, the delta from the slowest to the fastest is thousands of kilometers per hour. That's 1,300 miles per hour, supersonic flow. I'm going to move on to the moons because they're just as intriguing. Uranus's moons, its largest moons, had remarkable structure, remarkable albedo features, clearly some very interesting dynamics going on these moons. And we have only seen half of them because, as I said, we only saw half the system when Voyager flew by. And so our moon maps are incomplete. That gives you a sense of what they look like. We only see half. So there's much to learn there. Neptune's has a very active moon system, but the star of the Neptune system is its large moon Triton. Triton is a twin to Pluto, a twin in size, twin in distance from the sun, roughly. And except it was a Kuiper Belt object like Pluto, but it was captured in orbit by Neptune. It's in a retrograde orbit. So it's a rotating backwards. It's a captured Kuiper Belt object. And most exciting is that it had active cryovolcanoes literally erupting on the surface of the moon when Voyager flew by. Those black streaks you see there circled are active cryovolcanoes. The large one circled in the top shows you a little, the base of the volcano, a tall plume, and then a streak being blown throughout Triton's variable atmosphere. 8 kilometers this plume rose before the winds captured it. We would love to go back and see what this surface looks like right now today. Both of these planets have fabulous ring systems, and not only are they very complex in detail, but they change with time. We've learned that. We've discovered new rings since the Voyager flyby. We've discovered that the rings are colored. And if you want to ask me questions about that, I'm happy to talk about that. They're red, they're blue, they're gray. Very interesting stories behind that. Neptune's rings are not complete rings. They're clumpy rings. And here's some Voyager pictures of the arcs. This is sadly our best ground-based image ever of the rings. Off to the right-hand side, you see Leverrier and you see atoms and you see their arcs. It's not a very good picture. You wish they were better. We try. Here's a Hubble image, again, showing the ring arcs, not much better. We must send a spacecraft there to really study these rings in detail. And the magnetic fields are certainly unusual as well. This is Earth's, Jupiter's, and Saturn's through basic dipole, roughly aligned with our rotational axis. Not so for Uranus. Uranus's field is, the dipole is tilted 59 degrees from the rotation axis, and it's offset. When we found this with Voyager, we thought, maybe the giant collision that knocked Neptune or Uranus over on its side created that. But in fact, Voyager found that Neptune's field is just as strange as Uranus's field. And so it probably was not something to do with a collision or formation, but rather to do with the interior of the planet. We think that magnetic field is likely generated at that briny, icy mantle of ammonia water slush that I mentioned. So briefly, interiors, I'm going to show one slide here because the bottom line is we don't know what the interior is. We don't know if they're gradients. We don't know if they're shells. We don't know what their composition is. It's really important that we get a spacecraft out there to find out. And so let me talk about our plans for future missions in my remaining 1 minute. Our US decadal survey talked about Uranus orbiter. It was really both, but we were talking about one specific decade, so they talked about Uranus. But it was 3rd place after Mars and Europa. All right, so we're waiting. We are doing a new US planetary decadal survey right now with many papers about ice giants. And so fingers crossed, we are all hoping that this is finally the era for going back to the ice giants. It's an international endeavor, and I want to stress that. Almost the last conference that I went to before the pandemic was the Ice Giants meeting held in London. And so some terrific work was done there. I'm looking forward to working all of my UK colleagues on future exploration of the ice giants. I want to mention Webb because we're going to use Webb to look at the ice giants, and it's going to launch next year. And I want to talk about 2 mission concepts that we do plan to launch, both Trident and Neptune Odyssey. One focuses only on Triton, but the other is a Neptune system explorer. I'm very excited about it. I'm out of time, so I'm going to stop here and turn this over for questions, but thank you for the opportunity to talk about the ice giant systems of Neptune and Uranus. I can't hear her.
Thank you, Heidi. That was really fascinating, and some fabulous images there. I'd say it's also a first for the Appleton Conference that we have a cat co-presenting a talk. So that's really nice to see too. I have a few questions that have come in, and a reminder to the audience, if you have any questions, just to use the Q&A button to post them. One of the questions was about the popcorn clouds. So what are they, and why are they called, who called them a popcorn cloud?
We call them popcorn clouds because it kind of looks like a bowl of popcorn up there in the polar area with just lots of little dots of clouds. It isn't organized circulation like we see in other parts of these planets. Saturn had them as well. If you look at the northern pole of Jupiter, you see similar situations where these cloud appearances like that. To our very limited views that we have, you saw the best of what we have. They look like the tops of cumulus clouds bubbling up from a deeper layer. So at this point, that's all I can say. If we have an orbiter that is able to do imaging of the northern or southern polar regions, they may turn out to be coordinated cloud systems like we see on Jupiter with the Juno spacecraft, but we simply don't know. It's one of the mysteries that we didn't even anticipate. Voyager didn't see those. Voyager only saw the southern hemisphere, which was at that time enshrouded in haze. And so this was something new since Voyager, something that a new mission will have to explore.
Thanks. The question here is from Stuart Eves. What do you think of claims that William Herschel may have spotted Uranus's Epsilon ring in the late 1700s?
Yeah, I've seen those claims. All I can offer is that I think it would have been extraordinarily difficult to do that. I've been studying Uranus for close to 40 years now with a variety of telescopes from 24 inches up to 10 meters in diameter. And we typically can only see those rings at near infrared wavelengths when we can suppress the light from the planet. Hubble can see them as well, but it's and that's a 2-meter telescope, but it's extraordinarily difficult. So I think it might have been very difficult for Herschel to have done that. My only, if you want me to imagine something, maybe there was a collision in the rings of 2 bodies that temporarily put up a lot of fine dust that may have made them temporarily more reflective. I mean, we can wave our arms and speculate about that, but I think
potentially very impressive. We've had a question come in several times actually from the audience, which is, can you tell us a bit more about the colored rings, what the origin is of the colored rings?
Yeah, I'd love to talk about that. So most of these rings are gray or reddish. Reddish is not surprising because materials that are icy, dirty materials sitting out exposed to radiation and sunlight, they tend to redden with time. So that's not a surprise. The blue ring was a huge surprise. And, I showed that picture, which was Saturn and Uranus. Saturn has a blue ring, but the moon Enceladus is embedded in that blue ring. And Enceladus, on Saturn's moon Enceladus, is shooting out water, fresh water from its southern pole. And that is what we believe is causing the blue ring around Saturn, is that fresh water. But Uranus, there is a tiny moon embedded in its blue ring, but that moon is MAB and it's tiny. And we don't think it is big enough to hold a water ocean. So it's a mystery. I mean, I don't know. I think it could mean that it's a very fresh ring, but that could be why it's bluish. But we need a spacecraft out there to do some high resolution spectroscopy to really tell.
Yeah, very exciting. It's obviously aroused a lot of interest. One last one then from the audience, from Alam Abdi. In regards to Uranus's newly discovered rings, were they just missed initially or were they newly formed?
That great question. Thank you. We think that they were just missed because they're very faint. And we really worked, and also we were able to find them at the ring plane crossing. To bring Uranus in here, that's when the rings were sideways to us. And so their optical depth was much greater, and that allowed us to detect them, as opposed to when they were open with very optically thin, we couldn't see them as well. And so I think it was just a trick of the light that allowed us to detect them in 2007, in that time period.
That's great. Thank you so much for the insight into the distant planets you've given us. Thank you very much, Heidi Hammel.